In the late 20th century, progressive rock and alternative punk coalesced into a new genre, math rock. To start, let's put ourselves in the mathy ambiance by listening to a bit of Chinchilla by the band TTNG. Try to find the meter as you listen. For the record, the verse has groups of 11 plus 13. As you may have just heard, math rock contains extensive use of asymmetrical time signatures and frequent shifts in meter. The obsessive counting involved in its discourse is how the math rock nomenclature was formed. Coincidentally, the cyclic repetition of ostinati in math rock is aptly modeled by a mathematical equation, the discrete Fourier transform, henceforth DFT. In fact, the DFT assumes cyclic structures, giving it an analytical bias uniquely suited to study math rock's rhythms. I not only suggest that the DFT is appropriate for the genre, but that it represents a cognitively informed model of meter, modeling aptitude for metric entrainment. I've split the talk into 4 parts: a short introduction to the math rock genre, an explanation of the DFT, connecting the abstract mathematics to music cognition, a description of my methodology, and an analysis of excerpts from 3 math rock songs. In doing so, I hope to add to the growing discourse of rhythm and meter by examining an underrepresented musical style through a new theoretical lens. So, what is math rock, and where did it come from? While any stylistic genealogy is complex, we know for sure that the earliest math rock bands were inspired by progressive rock bands like King Crimson and Yes. Math bands like Don Caballero and Chavez are some of the genre's first flagships and represent an earlier style more akin to post-rock. Many recent math rock bands, however, are adapting the math emo nomenclature and even attract a similar fan basis. The term emo comes from the DC hardcore scene in the mid-80s, short for emotional hardcore. As scholars have defined it, one defining characteristic of the contemporary emo genre is its timbral twinkle in the guitars. But as the emo style gains popularity and becomes more widespread, its sound becomes less ubiquitous. If you're interested in exploring the math rock/emo style, I've attached a short Spotify playlist to the handout that you can check out. For now, I'll be examining 3 bands which lean toward the emo side of math rock. I'll be examining 3 math rock songs: Never Meant by the indisputably most influential 4th wave math emo band, American Football; Pool by the all-femme Japanese band Trico; and Cat Fantastic by the UK band TTNG. We'll be using the DFT to examine rhythms in these songs, so first I'll explain what the DFT is and how it works. The DFT converts a signal or input into its sinusoidal components. I won't discuss the math here, but if you're interested, the online handout has a color-coded equation. Essentially, the DFT's task is to break down and retrieve information from a signal, and ours, as interpreters, is to relate these individual elements to the whole. While the algorithm for the equation has been around since the early 19th century, in music theory, its introduction started with David Lewin. David Lewin was the first to propose using the DFT in music theory in 1959. However, the DFT remained untouched by music theorists until Lewin himself returned to it in 2001. Ian Quinn and Clifton Callender picked up his torch and were the first to explore the DFT extensively. Since then, the DFT has been applied and discussed in various contexts as shown on the slide here. Only recently has the DFT been implemented in the rhythmic domain. In order to calculate the DFT, we'd require some sort of input. Because this paper works with symbolic music, its input will be an array of numbers representing positions in time. To determine the number of non-trivial components resulting from the DFT, divide the length of the array by 2. So if we divide 4/4 into eighth notes, there are 8 positions and therefore 4 relevant components. Each one of these components corresponds with a division of the space into a respective number. So F4, the 4th component, divides a span into 4 parts. Because 4 is a factor of 8, this might also be thought of as a division into quarter notes. The more onsets that coincide with this division, the higher the magnitude for the component. A steady quarter note input has a maximal magnitude for an F4 here. On a perceptual note, I argue that the DFT is theoretically similar to Edward Large's neural oscillator model, a model based around neurons firing together when we entrain. Like the DFT, in Large's model, as more onsets align with the same periodicity, the higher the magnitude for that periodicity. As an analogy, Large and Jones show a rolling circle symbolizing our attentive state. We can directly map an entrainment oscillator to a DFT component with some simple trigonometry. So, in a cognitively aware way of thinking, the DFT components are represented as a series of rolling circles at a certain subdivision. Each component, therefore, represents a particular attentional state. Throughout the presentation, I'll change between the various representations of DFT components. Just know that they're all equal. The DFT components occupy an interesting theoretical space, conceptually sinusoids dividing the space, subdivisional projections in the music, or attentional states in entrainment, a three-faced coin. And that is cockatoo, the entraining, or that snowball, the entraining cockatoo. For a DFT example, let's do a quick walkthrough on our favorite overly theorized rhythm, the Traceo pattern. An almost triplet. It goes like dot, 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 dot. According to the DFT, the rhythm is a maximally even distribution of 3 into 8. I call these visualizations on the right rhythmic profiles. Each one of the components on the x-axis represents a division into that many parts. The third component divides the measure into 3 parts, so we can consider the magnitude on the y-axis to represent a goodness of fit, or as how well the stimulus can be fit into a certain sinusoid. So that was the theoretical backing. But just as important, we need to decide how to organize the rhythms we'll be examining. This is where the methodology is needed. The methodology is how we frame the musical object before analysis. We might say that the theory of this paper is formed epistemologically on connecting the DFT to cognitive theories of entrainment, and that the interpretive results are guided by how the methodology encodes the musical object. For now, I'll discuss the specific weighting implemented here. In this paper, I've implemented a rule-based system based on Lerdahl and Jakadov's metric preference rules and the internal clock accent rules from Pavlinessen's 1985. The rules take a rhythm and systematically derive an accent profile from it. I won't go over each rule here, but they're located in your handout. So, using this unfamiliar Mozart example, we go through the rules and we derive an accent profile. Like so. So after going through each parameter, the rhythm is described in terms of an array that we can use the DFT on. Let's listen with that in mind. Now what I find interesting here is that while the general meter is conveyed merely through events, the weighting isn't a great representation of the Mozart example. I think these rules are great for math rock, but not so much for Mozart, implying a difference in listening to different styles. Now let's put the methodology to use with an analysis of American football's Neverment. The iconic beginning of Neverment starts with a little intro before 6 rim clicks lead in to the lead guitar. You may have noticed that in the accent profile, I've intentionally left out drum patterns due to their clear paradigms to evoke certain meters, which is something we might want to discuss in the Q&A. That's what I wrote down for the original talk. If you have any questions about the weighting profiles or drum pattern things, you can always shoot me an email, put something in the comments. Per the guitar, I hear the lowest notes in the pattern sticking out, and after calculating the accent profile, the array generally shows that too. So now we use the DFT on the array, and it results in the following rhythmic profile. There are 4 peaks corresponding to the divisions of the rhythm into 3, 6, 9, and 12 parts. Because components 3, 6, and 12 are factors of the rhythm's 24 eighth note length, they correspond to notational subdivisions. The high magnitude for these components suggests that the rhythm projects whole, half, and quarter note pulses. In other words, the DFT is therefore implying 3 measures of 4/4 for the pattern. Returning to the song, after the pattern of the lead guitar is looped 4 times, the second guitar enters and stacks another cycle on top, spanning 24 eighth notes again. Let's listen and pay particular attention to the lower line of the second guitar. That lower line projecting 7 plus 6 plus 7 plus 4, which I notated below, in eighth notes really sticks out to me. And again, the weighting does show that. In the rhythmic profile, there are peaks around components 4, 7, and 10/11. The fourth component is high because the projection of 7 plus 6 plus 7 plus 4 is a nearly even division into 4 parts. On this clock, you can see that the lower line occupies positions 0, 7, 13, and 20, which is very close to an even division, 1, 7, 13, and 19. So it's really only 2 onset shifts away. So let's listen again and see if you can hear how the bass line is nearly even. Even if it's offset a bit, the lower notes feel like they're afterbeat syncopations, dividing the span into 4. The 10th component doesn't correspond with an integer subdivision. It corresponds to 2.4 eighth note projections, which doesn't musically make sense. Instead, we might interpret this as an approximation between 2 projections, or an average between the 2, the quarter note and the dotted quarter. In other words, competing subdivisions, so it's representing a metric conflict here. To represent metric conflict, Rick Cohn introduces a visual which divides the length of the meter into its duple and triple subdivisions, a metric ski-hill graph. The ski-hill graph can be directly mapped onto the DFT components. Not only that, but because each component has magnitude, it can quantitatively show a depth to how much a subdivision or conflict is conveyed according to our accent profile. In other words, it creates a topological surface with gradients and degrees rather than a binary present or not. Reviewing never meant the rhythm is a near even division into 4 parts, and at a lower level it has a metric conflict between the quarter note and dotted quarter. Let's just listen one more time and see if you can concentrate on one of those. In 2010, guitarist and vocalist Ikumi Ikkyu Nakajima formed the band Trico. A 2015 issue of the Rolling Stone entitled 10 New Artists You Need to Know has described them as adrenalized math rock. This is the beginning of Pool off their album The. After a short introduction, the guitar projects a grouping of 5 and repeats that grouping 3 times, making a cycle of 15 8 notes. The DFT of the array yields a rhythmic profile here. It picks up on the 5 projections in F3 and also shows a high magnitude for F6. F6 corresponds to a further division of the 5/8 into 2 parts, showing the inherent back and forth in the subdivisional conflict of a 5/8 meter. After the guitar, EQ then enters with a voice part, repeating a grouping of 10 3 times, making a cycle of 30. The 10 projections are split into 3 plus 3 plus 2 plus 2. The DFT unsurprisingly picks up on the 10 projections in F3 and shows an underlying quarter note subdivision throughout. But interestingly, there are peaks at F9 and F12. Both components F9 and 12 represent the division of the 10/8 measure into 3 and 4 parts respectively. This shows that the rhythm 3 plus 3 plus 2 plus 2 is structurally close to a maximally even division into 4 parts, 3 plus 2 plus 3 plus 2, and 3 parts, 3 plus 3 plus 4. This suggests more obviously that the projections of 3 and 2 are prominent, both vying for or perhaps sharing the role of tactus. An isochronous interpretation of non-isochronous meters, like the DFT, therefore shows the average of the competing subdivisional projections. Finally, we turn to TTNG again, their song Cat Fantastic. Examples thus far have been strict ostinati, so let's look at an example which complicates that. This bridge starts with a solo electric bass and is later joined by a melody doubled in the voice and guitar. Oh, we got a cat here. Let's listen. So this bridge repeats 3 patterns of 7/8, followed by a measure that changes with each iteration. For every iteration, the altered measure on the end adds an extra 8th note, moving from 3/8 to 4/8 to 5/8 and finally to 6/8. I call this a Milankovitch cycle, named after an astronomer who first described the cycles that change over time in different orbits. Somewhat poetic here. Your handout shows the rhythmic profiles on each iteration of the Milankovitch cycle calculated with the bass line and voice line. Despite the slight variations between each iteration, each profile retains the same general shape. They have peaks that roughly correspond to the 7/8 measure, an asymmetrical division of that into 2 parts, and a further division. In this way, the profiles resemble our common metric hierarchies. The rhythmic patterns in the first and third iteration are essentially identical, and their rhythmic profiles show that too. There is one significant change in the profiles, though. Due to the extension of the extra measure, the pattern gradually develops a larger scale symmetry. Notice as the cycle continues to grow, the pattern approaches a larger 2 and 4 part symmetry. So, in the smaller cycle, A, meter and hypermeter are lumped together. But in the larger cycle, the meter and hypermeter become untangled. I think this feature captures the phenomenological experience of the progressions process. The 3/8 slowly snails out, and as it stretches, it alters the symmetry of the cycle and therefore shapes our experience of it. Let's listen one more time and focus on this sprawling symmetry.
Gather the right minds, and slowly through time, all the right minds, ignoring patience that we lack, will inform the new minds, and likely in kind, all the new minds will in turn replace the old.
My argument situates the DFT as a mathematical equation appropriate for modeling a cognitive experience of meter, and does so on underrepresented music popular today. I've shown 3 math rock examples: Never Meant, which has metric conflict within a standard meter; Pool, which has metric conflict and near evenness despite its asymmetrical meter; and Cat Fantastic, a piece with changing cycles and asymmetrical meters. And I've shown how the DFT captures all of those features. While I've demonstrated how both Cohn's metric ski hill graphs and Large's oscillator model can be adopted and unified by the DFT components, the field of metric theory is vast, and this was only a foray into its troughs. Thanks for listening.